if you take yourself all the way back to geometry in high school or wherever you were, you might remember that the area of a circle with radius r is pi r squared, right? Simple enough. Hopefully that one's not that surprising to you. And what you might remember and you might not remember is that if you took a sector of a circle, so instead of the whole circle here, you just took some sector, some region, that the area of that sector is 1/2 times theta, which is the angle width, r squared. Now this is pretty simple. If theta is 2 pi, which means that that goes all the way around, so it's really just a circle. If you plug 2 pi in here, the 2's cancel, you get pi r squared. So what it is it's really just a proportion of how much of the circle you've covered. Now another thing to remember is theta needs to be in radians. If you're trying to plug in like 90 degrees there, that's kind of nonsense. You're going to get a not useful answer. So make sure when you do this that theta's in radians. But we're not dealing with high school geometry here. We're dealing with polar coordinates, specifically with calculus. So what I want to do is I want to look at a region that looks like this. I want to say, hey, if I've got those polar lines, theta equals alpha and theta equals beta. Now, hopefully you remember from polar coordinates that the r's are these concentric circles of different radii. That's what the r's are. And thetas are those lines that always maintain the same angle with respect to this axis, right? So at any given point, that angle from the axis up to that line is theta, and the angle from this to this line is beta. So we're going from alpha to beta. But in this particular case, notice that we don't have like a circle, we don't have like a sector. What we have is some sort of curve. And if that curve is a function of the angle, so what you're really saying is that at this angle, the curve is that length. Or the curve, I'm sorry, the distance to the point is that. At this angle, the distance to the point is that. At this angle, the distance to the point is that. So you're basically saying that as theta changes, I can create a function that gets me what my distance to that point is. So ultimately, everything's a function of theta. If you do that, which is what we do all the time, by the way, with y's and x's, right? We say y is a function of x, which basically means I can get the y value if I have the x value. It's the same thing here. I can get the r value if I have the theta value. If it's set up like that, then we can apply an extremely similar relationship. This is 1/2 theta times r squared. This area is 1/2 the integral from alpha to beta of really what is r, which is the function of theta squared d theta. It's actually really simple, I promise. What you want to do when you do this sort of thing is you want to find the starting angle and you want to find the ending angle, and then you want to write an expression that gets you the length as a function of theta. So if it was like r equals sine theta, well that tells me what r is. If I know what theta is, I can get what r is. And that's what we're doing here. So this would be, again, if it's r equals sine theta, what goes in here is sine theta. And then you just integrate. Notice that in the case where r is a fixed value, right, r is a constant, this would be 1/2 this r squared d theta, which really is just 1/2 theta r squared. That's how it comes out. So it's really, in the case of a circle or a circular style region, it's just this. But this is a more generic formula, and we're going to apply some examples. I'm sure it'll make a lot more sense once we get to there. But this is the general rule. FYI, the function needs to be continuous and non-negative. The reason being is if it gets to be negative, then you're not really going from this angle to that angle, right? If you're negative, you're actually over here. So your angle is going to be different. So make sure when you set this up that your function output is never going to be negative, or this is invalid.